I'm presenting to you my PhD study titled Laser Pinning Effects on Mechanical Properties of Aluminum Lithium Friction Stir Welded Joints by Crystal Plasticity Modeling and Quantitative Evaluation. Uh, First, I'm giving you an introduction of the research work, then I'm introducing the CPFM framework for the aluminum lithium alloys, and then physics-based CPFM for predicting the mechanical properties of aluminum lithium FSW joints and laser pinning effects on improving their tensile and fatigue properties. Now the introduction. Aluminum lithiums have been Aluminum lithium alloys have been a crucial part of aerospace industries because of their high strength to weight ratio, advanced stiffness, modified cryogenic strength, and good weldability compared with conventional aluminum alloys. Precipitates are the major strengthening microstructure features in these alloys, and these alloys have been functionalized in the aerospace industries such as airplane structures, cryogenic rocket fuel tanks, and satellite service modules. Friction stir welding is a solid-state joining process that leads to no joint melting occurrence, no alloying element loss, low tensile residual stresses and distortion, and no filler material required, which leads to the lightweight, and it leads to higher mechanical properties than conventional fusion welding for aluminum lithium alloys. It's been functionalized in the industry such as the airplane cargo ramps and satellite pressure vessels. However, the dissolution of precipitate phases during the thermomechanical effects of friction stir welding leads to the degradation of joint mechanical properties such as the hardness, tensile strength, and fatigue properties in the joint center. So it's necessary to improve the joint mechanical properties by post-welding processes. Surface treatment methods have been utilized to improve the mechanical properties of aerospace components such as shot pinning, roller burnishing, and laser pinning, among which laser pinning induces deeper and more stable compressive residual stresses with lower surface damage and high controllability. In this process, the high energy laser vaporizes the sacrificial coating layer on the material surface and turns it to a rapidly expanding plasma, which is then confined by a transparent layer to amplify the laser shock pressure. The specimen usually is controlled by a robot arm to ensure the uniform laser treatment on the targeted surface. This process has been functionalized in the aerospace industry, such as gas turbines and aluminum aircraft fuselages. Several research work have been experimentally investigated the laser pinning effects on the aluminum FSW joints, and they have reported the increase in joint surface hardness, tensile properties, and fatigue resistance. So laser pinning is proven beneficial for improving the mechanical properties of aluminum FSW joints. However, the contribution of microstructural effect on material mechanical property enhancement cannot be clarified by the experiment. For this purpose, material modeling methods are required to quantify the strengthening contributions of microstructural evolution under laser pinning. Dynamic modeling of laser pinning in the macro scale has been developed to predict the laser shock pressure history as well as the material plastic deformation under laser pinning and the resulting residual stresses in the material after laser pinning. However, macro models do not include the effects of microstructural features as the origin of material deformation behavior. For this purpose, microstructure sensitive modeling methods are required to quantify the microstructure effects on the deformation mechanism. The CP model, crystal plasticity model, considers the crystal slip behavior as the source of material deformation, and CPFEM incorporates the microstructural features in the material modeling, such as grain texture, crystal morphologies. This method have been developed to predict the microstructure sensitive material tensile behavior and variations in the fatigue properties. Also, this process have been developed for the shot pinning process to predict the shot pinning induced residual stresses and its relaxation after the cyclic loading. However, the strengthening effects of microstructural evolution are not evaluated in the mechanical property variations in this process. For this purpose, physics-based CPFEM is required to quantify the strengthening contributions of microstructural features during the material processing. Physics-based modeling has been developed previously to predict the yield strength, local yield strength of aluminum lithium FSW joints. Moreover, the strain gradient physics-based modeling methods have predicted the dislocation density-based hardening for the stress-strain behavior of material under laser pinning and the resulting dislocation density evolutions and the residual stresses under laser pinning. To summarize the literature, CPFEM has been introduced to predict the microstructure-sensitive material deformation behavior. CPFEM shot pinning model has predicted texture effects on the shot pinning-induced residual stress distribution, and physics-based modeling methods also have been developed to predict the FSW joint local yield strength. However, no research work has predicted the microstructure-sensitive mechanical properties of FSW joints, and no study has also quantified the laser pinning-induced strengthening mechanism from the microstructure wise to predict the joint tensile property enhancement, and no study also has obtained microstructural evolution effects under laser pinning on the joint fatigue property improvement. In this research, we developed the physics-based CPFEM model to quantify the strengthening contribution of microstructural variations such as precipitate phases, grain size, dislocation density, and crystal morphology during the material processing such as FSW and laser pinning to predict the resulting mechanical properties such as tensile strength, fatigue strength, failure mechanisms, and mechanical property heterogeneity. For this purpose, initially CPFEM framework is developed for aluminum lithium alloys to predict the mechanical properties. Subsequently, the physics-based CPFEM is developed to predict the microstructure sensitive mechanical properties of FSW joints of aluminum lithium alloys and the laser pinning beneficial effects on their tensile properties and fatigue strength. First, the CPFEM framework for aluminum lithium alloys. In this study, CPRVE or CPFEM models are developed by extracting the microstructure, crystal texture, and grain morphologies from the EBSC process and calibrated by the mechanical properties from the tensile tests. And the developed model can predict the texture-induced anisotropic tensile properties on the rolling and transverse direction and the grain boundary effects on the stress-strain heterogeneity in the CPFEM model. For the experiment, EBSC obtained the material microstructures such as grain texture, crystal orientations, and grain boundary misorientation. Samples are polished and vibration polished prior to the laser pinning, prior to the EBSC test, and the EBSC test is conducted with a NOVA Nano SEM machine. Tensile test also measures the tensile properties along the rolling and transverse direction to obtain the anisotropic material properties. CP modeling includes considering the crystal lattice rotation and slip as the source of material elastic plastic deformation. It calculates the plastic velocity gradient, critical resolved shear stress, which is the slip strength, and flow rule, which defines the slip shear strain rate. And the CPFEM model includes the crystal texture and grain boundary effects into the microstructure sensitive model. For CPFEM development, 2D CPRVEs are developed towards rolling and transverse directions, and material microstructure is synthesized by the DREAM 3D software into the CPFEM model, and loading application is simulated by the strain controlled loading on the CPRVE models to simulate the tensile test. For the CPFEM results, firstly, the model mesh convergence ensures the accuracy and efficiency of the CPFEM models by adjusting the grain numbers and elements per grain numbers. Tensile property prediction shows that CPFEM can predict the microstructure sensitive anisotropic tensile properties is consistent with the experiment. And then the model can also predict the stress-strain heterogeneity and the high gradient at the grain boundary effects. As for the overall conclusion, CP model can predict the microstructure sensitive material deformation behavior. The developed CPFEM model can predict the texture-induced anisotropic tensile curves of aluminum-lithium alloys towards rolling and transverse directions, and the model can also predict the polycrystalline deformation behavior by including the interaction between neighboring grains with crystal misorientation. Now the physics-based CPFEM model for aluminum-lithium FSW joints. In this study, joint local physics-based CPFEM models are developed by including the material microstructure attributes such as crystal morphologies, dislocation density, precipitates, and the developed model quantifies the strengthening contribution of these microstructural attributes to predict the local and global tensile properties of FSW joints. For the experiments, FSW process parameters are set for the optimum welding joint mechanical properties, and 5 millimeters thickness, thick aluminum lithium 2195 in the T6 condition sheets are joined together in a butt joint configuration perpendicular to the sheet rolling direction. TM tests are conducted and the Talos F200X TM device is utilized for the TM test, which shows like precipitation types and dislocation, and you can also figure out the grain boundary effects in the TM test. And the DIC test include the DIC method measure the joint tensile local and global tensile properties. They include the low strain rate to secure the homogeneous deformation throughout the joint. The random black dots spread on observation surface for the camera to observe the material deformation, and CCD camera for the process observation. And for DIC analysis, the match ID software obtains the strain maps from the initial condition in the tensile test of the joints to the UTS, and iso stress assumption is also used to obtain the stress-strain curves from the DIC results. Physics-based CP modeling includes the slip strengthening effect of precipitate phases, dislocation density, and grain size, and it considers the total critical resolved shear stress, which is the total slip strength, as the summation of each of these independent effects. And finally, the plastic hardening, which is the uh, variations in the dislocation density during the plastic deformation. For the CPFM development, firstly, the micro-hardness test showed low variations in the mechanical properties through the thickness, and the average values in the can be seen in the midsection of the joint. So the joint local CPRVs are considered at the midsection of each zone at the mid-thickness of the sheet. And the homogeneous mechanical properties are assumed for each zone. It means the mechanical properties are at the CPRV model is assumed to be homogeneously distributed in the corresponding zone. And the tensile tests are simulated for both CPRVs and the macro model of the joint to obtain the local and global tensile properties of the FSW joints. From the EBST results include the elongated grain texture with noticeable amount of low angle grain boundaries at T6 condition because of the high plastic deformation during rolling, and no significant texture evolution in HAZ compared with T6 under the thermal effects of the FSW, and noticeable grain refinement and high angle grain boundaries at TMAZ at SC at the joint center because of high recrystallization and plastic deformation, and texture randomization also is observed from the dominance of 1-1-1 planes at the BN. You can see completely randomized texture in the SC. TEM results include the large amount of T1 precipitate generating in the base material, which is the T6 condition, partial dissolution of precipitate at HAZ under thermal effects, and the higher precipitate dissolutions at TMAZ and SC because of the plastic deformation and higher temperature. And you can also see the dislocation pile up more noticeable at SC because of the plastic deformation under FSW process. And dislocation density results include the considerable amount of dislocation at the base material, which is the T6 condition, and partial alleviation of dislocation density at HAZ because of the thermal effects, and the increase in dislocation density at TMAZ and SC because of the plastic deformation. Also, the texture randomization can be seen from the dominance of 1-1-1 texture to relatively randomized texture at the joint center at SC. CPFM calibration include obtaining the strengthening microstructural physical characteristics such as precipitates and dislocation density, inserting the strengthening effect into the physics-based equation to obtain the slip strengthening effect, and adjusting model parameter to fit the simulated tensile curve to experimental ones for the O-state material without precipitate and the T6 condition to fit the simulated and experimental tensile test. And for the joint local mechanical properties, the SC has the lowest yield strength because of the dissolution of precipitates, but it has the highest hardening slope and total hardening amount because of its lower grain size. It's followed by TMAZ, which has higher yield strength because the precipitate still exists at TMAZ, and HAZ with the highest yield strength, but the hardening slope is lower because of higher grain size. Macro model prediction also show consistent result with the experiments, and the failure you can see occurs before the predicted UTS at SC locations, and larger strain values are observed at the welding joint center because of its lower yield strength, and we can see the stress-strain concentration at the TMAZ-HAZ border because of the mechanical property heterogeneity. And the tensile failure results from the experiment show higher average strain values at SC, but the failure occurs at the predicted stress-strain concentration area, which validates the macro-model results. And tensile failure happens at this location. For the overall conclusion, the developed physics-based CPFEM model can predict the local tensile properties of FSW joints by quantifying strengthening effects of joint local microstructure. The local loss of T1 precipitate phases and crystallographic texture randomization lead to a noticeable decrease in joint mechanical properties, and high stress-strain concentration at the HAZ-TMAZ interface caused by the joint mechanical property heterogeneity leads to early joint tensile failure. Now the CPFEM for laser pinning effects on joint tensile properties. In this study, joint local physics-based CPFEM models are developed by including the microstructure attributes such as crystal morphology, residual stresses, and dislocation density. This model will quantify the strengthening contributions of laser pinning-induced residual stresses, work hardening, and crystal texture variations to predict the improvement in joint local and global tensile properties after laser pinning. For laser pinning experiments, double-sided multiple laser pinning is applied on both sides of the joints up to 3 layers. At the joint center where lower mechanical properties were observed. The laser is applied with the power of 10 joules, which asserts the laser spot with the 4 millimeter in diameter on the surface, and laser pinning is applied with the zigzag pattern to cover all over the joint central areas. And subsequently, tensile specimens are cut from the laser pin samples. XRD method measures the multiple laser pinning-induced near-surface residual stresses. XRD tests are applied by the pulse text device, and electrolytic corrosion drilling is also used to reach the subsurface areas to measure the residual stresses in the subsurface. And cosine measurement method in the two-dimensional detection technique is used for measuring the residual stresses because of its lower errors compared with the conventional sine method. For the CPFEM development, CPRVE models are developed based on the assumption of homogeneity of the mechanical properties at each zone and the symmetricity about the joint mid-axis and the sheet mid-section to obtain the CPRVE models. And the loading simulation is applied on both CPRVE and the joint macro-scale models to obtain the joint the local and global tensile properties. And the eigenstrain method is utilized to simulate the laser pinning-induced residual stress. From the CPFEM predictions for the contributions of residual stresses, eigenstrain method can predict the multiple laser pinning-induced residual stresses, and similar overall residual stresses are observed for SC and TMAZ, and similar increase also is observed for the yield strength and UTS for both areas. For dislocation density contributions, dislocation density values are relatively steady throughout the depth before laser pinning, and they increase in near surface region after the addition of LP layers, and they increase relatively higher for the SC than TMAZ because of higher plastic deformation at SC because of its lower yield strength, and also its higher plastic hardening slope. As for the tensile strength, a slightly higher increase in yield strength also observed at SC than TMAZ, And also work hardening doesn't affect the material UTS, and it only increases the yield strength. For the crystal morphology contributions, the increase in 100 and 111 texture can be observed after laser peening. No noticeable effect is observed in the grain size. From the tensile property improvement, we can see similar improvement in yield strength and the UTS, just like the residual stress effect, and a slightly higher uh, improvement effects on SC than TMAZ because of the higher plastic deformation on the laser peening in SC. For the crystal misorientation contribution, we can see the decrease in misorientation angles under the multiple laser peening due to the crystal morphology homogenization towards 111 plane, and this has no noticeable effect on the tensile properties, but it has potential effects on the improvement in joint fatigue strength, which will be explained later. For the CPFM combined effect, we can see the CPFM can predict the improvement in the local tensile properties of the FSW joints at ST and TMAZ. Residual stresses contribute to the highest increase in the joint local tensile properties, followed by dislocation density, and the lowest one belongs to the crystal texture. And you can see as laser peening layers are applied, the gap between the TMAZ and HAZ tensile properties is also closing, which is the homogenization effects of laser peening. For the joint global tensile properties, macroscale model can predict the laser peening effect on joint global tensile properties, and higher, as you can see in this curve, uh, higher increase is also observed in the material yield strength than UTS because of the work hardening effects that only affected the yield strength, and the improvement in the joint tensile fatigue mechanisms. As you can see, before laser peening, we have a higher stress concentration because of the heterogeneity of mechanical properties, which is avoided by the addition of laser peening layers. And this one from the experiments can be seen that the failure location relocates from this border to the central area, which increases both tensile strength and elongation. For the overall conclusion, the developed physics-based CPFM model can predict the laser peening-induced improvement in joint tensile strength. The highest laser peening contribution in joint local yield strength belongs to compressive residual stresses, followed by work hardening and crystal morphology variations, and laser peening effects on the joint center improve the joint mechanical property homogeneity, which causes the improvement in both joint tensile elongation and strength. Now the CPFM for laser peening on joint high cycle fatigue properties. In this study, CPFM model is developed at SC, which is the failure location of the fatigue test, by including the microstructure effects such as crystal morphology, residual stresses, dislocation density. The developed model quantifies the effects of laser peening-induced residual stresses, work hardening, and crystal texture on the variations of extreme value FYP and also grain average FYP values in depth to evaluate the laser peening effects on the joint fatigue properties. For the high cycle fatigue test, obtain the multiple laser peening effects on joint fatigue properties, and laser peening is applied with the same pattern to cover all over the joint area, and fatigue specimens are cut from the laser peen samples. Fatigue tests are conducted with the stress control regime with the highest, with the maximum stress of 200 megapascal and the stress ratio of 102 up to the sample failure. For the HCF modeling, FIPs have been developed based on the critical plane approach to obtain the driving force for fatigue crack initiation and growth, reduce the computational cost of fatigue simulation, and predict the material fatigue loss. Different approaches have been utilized, such as a stress-like approach and a strain-like approach developed for FIP, among which the Fatemi-Saucier FIP parameters can reasonably predict the material HCF properties by considering the maximum normal crystal slip stress, cyclic stress, and the plastic shear strain as the mechanisms behind the formation of fatigue crack failure. And extreme value FIPs analyze the high cycle fatigue properties as regions with high probability of fatigue crack formation, such as the grain boundaries of hard and soft grains with the high crystallographic misorientation. FIP extreme value Gumbel distribution have been uh, developed to statistically characterize the HCF properties at grain boundaries with statistical parameters such as the UN, which characterizes the highest extreme value FIP in the population, and the alpha n, which the inverse measure of largest value dispersion around the maximum value FIPs. For CPFEM development, the the high cycle fatigue enhancement is evaluated based on firstly extreme value FIP variations at grain boundaries in the near the surface where the failure happens for the unpinned condition, to predict the laser pinning modifications in joint surface integrity, and then grain average FIPs to predict the high cycle fatigue property modification in depth and fatigue failure mechanism modification. For this purpose, surface CPRVs are developed to obtain the extreme FIP values on the surface and their variations with laser pinning, and half the grain average CPRVs are developed to obtain the grain average FIPs in depth after laser pinning to obtain the failure mechanism variation. And loading applications are simulated based on the experiment with the strain controlled regime with the highest stress of 200 megapascal and the stress ratio of 0.1 corresponding to the experimental HCF test. And the stabilized stress strain cyclic loading is considered for the calculation of FIP parameters, which represents the rest of the high cycle fatigue loading after the initial relaxation of the mean stress. And from the extreme value FIP results, you can see from the CPRVE, the stress strain concentration occurs in the boundary of hard and soft grains with the high amounts of misorientation, and the high accumulation of cyclic plastic strain is observed at these regions. And this leads to the extreme FIP value occurring at these soft hard grain boundaries, and shows the high fatigue sensitivity at the soft side of these boundaries. For the laser thinning effects on the extreme value FIP, we have from the statistical Gumbel distribution data, we have the residual stress as the main contributor to extreme value FIP decrease by evolving the Gumbel distribution parameters. It is followed by crystal morphology effect, which has the higher effect than dislocation density because of the decrease in grain boundary misorientation, and dislocation density as a lower effect. From the grain average FIPs, we have still the residual stresses as the main contributor to grain average FIP decrease, and then dislocation density induces higher effects from the magnitude and depth than the crystal morphology effect, and the high FIP values relocate to the deeper surface regions where the fatigue failure is more likely to happen after laser pinning, and still the highest joint local average FIP remain at SC area after laser pinning, which shows that fatigue location is less likely to change after laser pinning. The high cycle fatigue test shows the fatigue failure happening at ST for all laser pinning conditions, which validates the modeling results. And HCF improvement can be observed for both aluminum lithium alloy and these FSW joints, and it's more noticeable in the lower applied as cyclic stress, which shows that laser pinning has higher effect in the high cycle fatigue than the low cycle fatigue regime. And the relocation of FCI, which is the crack initiation, fatigue crack initiation location to further to the depth after laser pinning, which validates the grain average FIP value results, and higher ductile fracture also observed when FCI relocates to the depth, which is the effects of relocation of fatigue cracks to the depth on improving the laser pinning, improving the fatigue life. For overall conclusion, the developed physics-based CPFEM can reasonably obtain the laser pinning effects on improving the joint fatigue properties. Laser pinning induced high cycle fatigue strengthening factors include higher material resistance against cyclic plastic deformation under compressive residual stresses, dislocation density and crystal texture intensity, and the reduction of misorientation under the crystal morphology homogenization effect. And experimental high cycle fatigue results show enhancement in joint fatigue life by transforming FCI locations to the depth after laser pinning and validate the modeling prediction. Now for the summary and the future work, original contributions of this work include proposing FSW joint physics-based CPFEM to predict the joint mechanical properties by quantifying the strengthening contribution of joint local microstructure features, including texture, precipitate, dislocation density, and grain size. And the second one is developing the physics-based CPFEM laser pinning model to quantify the laser pinning strengthening effects on the enhancing joint tensile properties by quantifying the strengthening contribution of laser pinning induced microstructural evolution such as residual stresses, bulk hardening, and texture variations, and developing the physics-based CPFEM fatigue model for quantitative evaluation of laser pinning effect on improvement of joint high cycle fatigue properties by quantifying the microstructural contributions on the FIP values. For the future work, the current model utilizes the experimental measured joint local microstructure to predict the joint mechanical properties. But, however, the physics-based CPFEM model can be further developed to quantify the effects of FSW parameters on the joint local microstructure variations to optimize the joining process. In the current work, laser pinning effects on microstructural features are experimentally measured after laser pinning to use as a model input. However, a high strain rate physics-based CPFEM dynamic model can be further developed to predict the laser pinning-induced microstructural evolution for the surface modification optimization. And finally, the current approach predicts the laser pinning effect on the mechanism behind FCI fatigue crack initiation relocation to the subsurface. However, the model can be further developed to predict the impact of FCI depth on the fatigue life improvement by modifying the FIP equations.